Hey guys, thanks a lot for coming to my session. My name is Jacek. I work at JIT Solutions as a big data consultant. Today, hopefully, I'll give you a brief overview of Hadoop as a platform and its big data capabilities. Before we start talking about the technical aspects and details behind Hadoop, it's perfectly valid to ask ourselves the following question, which is, what do we really need Hadoop for? So as you guys are developers, you perfectly know that there are many existing tools on the market, like BI tools, NoSQL databases, many relational database engines which can store even petabytes of data. So where does actually Hadoop fit in this context? So to answer that, it's, I think, important to understand what was the motivation behind Hadoop and what its creators had in mind. Now, to answer that, I think it's worth looking at how the hard drives have evolved over the last, let's say, 30 years. So back in 1990, it was quite common for your PC to have a hard drive with the following specs. So 1.37 megs of capacity, and the discrete speed of 4.4 megs per sec. While 20 years later, so a year before the first release of Hadoop, you would have somewhere around 1 terabyte of capacity and 100 megs per sec when it comes to the discrete speed. Well, you can obviously tell that it's a huge leap, especially when it comes to capacity, but there's quite an interesting statistic behind it. So when it comes to the 1990s disk, over a course of just a single second, you were able to read the whole disk 3 times. While when it comes to the more modern disk, it would take 2.5 hours to read the whole disk only once, which is a huge difference, as you can tell. This really brings us to the answer, like what is the current trend when it comes to computing, which is making the processing of data in a more distributed way. So instead of using the scale-up approach, in which we would just have a single processing machine, a single server, and we would just add more RAM, more processors if we wanted to scale our system. In the scale-out approach, we're just adding an extra node, or 1 or 2 or more, and then we're trying to maintain a linear scalability when it comes to our computing power. And this is exactly the approach that Hadoop is trying to follow. So let's start with the basics of how HDFS, so the Hadoop distributed file system, is implemented. So in a Hadoop cluster, we have 2 types of machines. First of them is a name node, and the other one is a set of data nodes. So what's the difference between them? A name node is a machine in the cluster which stores the references, the metadata, all the physical addresses of all of the blocks of the files that we have in the cluster. While a data node is a machine which holds the physical files and also does all the computing on our cluster. By default, every block of file on Hadoop is replicated 3 times, which means that if we were to lose one of the data nodes, we would be still left with 2 copies of the file, and in that case, our cluster would be automatically rebalanced. So one of the copies of the files would be also transferred to another data node, so the storage on all of the data nodes would be more or less maintained. A similar thing would happen if you wanted to scale our cluster and add more nodes. Then in a similar fashion, Hadoop would just move some of the blocks to the new, clean data nodes, and therefore attempt to keep all the data nodes more or less balanced. And this is how Hadoop is trying to achieve its resilience by replicating the blocks of files and also making it easier for computing in a distributed way later on. So whenever we want to read a file, do some processing on it, and let's say an HDFS client connects to the cluster and makes a request to the name node, which then gets back to us with with a certain address of a file on which we want to do the processing. When it comes to the production environments, having a secondary name node is an absolute must because if we were to lose the name node, then we wouldn't be able to retrieve our data and serve any requests to the clients. So therefore, especially in production environments, we have a secondary name node which is just constantly being synchronized with all the changes done to the name node and the HDFS as well. Now that we have a little background on how HDFS works under the hood, it's worth to mention that Hadoop, as its core, it's not just an implementation of a distributed file system. Hadoop core, since it's version 2.0, also ships with Yarn, which is a resource manager for the jobs run on the cluster. So it does all the scheduling and the actual execution, creating the containers for the applications on the data nodes, and so on. Hadoop also ships with an implementation of the MapReduce paradigm. And if you guys are familiar with Scala or you programmed with streams with Java 8, you probably know well what the MapReduce paradigm is. In the context of Hadoop, it's just the distributed implementation of that very same model. Around the Hadoop core, we have a huge number of open source projects, only about 50 in the Apache Foundation itself, that help you develop applications on Hadoop. So the different ones connected to data ingestion, distributed programming, machine learning, orchestration of your jobs on the cluster. One of the most popular ones in the recent years is, for instance, Apache Spark. And it's actually a distributed programming model that is actually superseding MapReduce when it comes to performance and ease of development. And because of the fact there are so many projects in the Hadoop ecosystem, it's sometimes really hard to maintain the cluster yourself, do all the versioning of the projects. And this is when using commercial distributions of Hadoop comes pretty handy. So at Nordea, in the project where I am currently assigned to, we use Cloudera, but there are other popular ones like Hortonworks and Mapr. So what these companies do, they just prepare packages of different Hadoop distributions and related projects, and they ship it to you, and also they provide enterprise support, of course, if you pay for that. So now that we've seen just a very narrow selection of Hadoop-related projects in the ecosystem, and it can be for sure confusing enough, let's maybe follow a certain business case how Hadoop could be implemented maybe in an organization like yours. So for the sake of that, of the example, let's assume that we're working for the Infoshare bank, which is a major international bank, and started to have issues with scaling its data processes. And just to make it easier to understand the examples, we're going to assume that, like every other bank, the Infoshare bank has a transaction system which stores such information as account balances, all the records on transfers, and we're also going to include the ATM deposits. And we're going to go for a few business cases, like ingesting the account records on a daily basis from that database to Hadoop, streaming all data on transfers and ATM deposits, allowing interactive querying of data on Hadoop. And last but not least, I'm going to show you an example of a Spark code on how we can generate files based on the data we have on Hadoop, and we're going to export it to an external database. So let's go through the challenge number one, which would be ingesting the account data from the relational database to Hadoop. Now, when it comes to doing simple ingestions from external databases or data warehouses to Hadoop, or the other way around, Apache Sqoop is a really simple tool to use to. What Sqoop is basically a command line tool that just wraps MapReduce code under the hood and allows you to perform certain import or export operation without writing any complex Java, Scala, or Python code. So following our example, in order to import something from an external database to Hadoop, we need to invoke a following command. So it will be a Sqoop import. We need to provide such parameters as the connection string, username, password, name of the table in the database. The --m parameter is the number of mappers that we wish to utilize in our operation. The next parameter is a where clause on which we want to filter our records in the database, which is optional. And the last parameter is the target directory on HDFS to which we want to write our data. So once we're done with that, we can actually browse our data on Hadoop. And Hadoop core also ships with a number of Unix-like commands which you can use to interact with HDFS. So in that case, we're just listing the contents of the directory to which Sqoop has written the output. And you can see two files there. So every time a yarn job succeeds successfully, it writes an empty file called _success, which can be just a flag for your automated processes that everything went well. And the other file, obviously, is the actual result of the job, which is just a CSV file with a dump of the records from our MySQL database. So now that we have imported some data to Hadoop, let's make it easier to read, let's say for an analyst, not essentially a developer or a DevOps guy that knows all the fancy Linux commands. And for that particular case, there's a project called Apache Hive, which will be perfect for that. And what Apache Hive is an SQL interface on HDFS. So once you create that level of abstraction on a certain directory in Hadoop, it allows you to query your files in an interactive way using an SQL-like language. And Hive was actually developed at Facebook to speed up the development on Hadoop. And fortunately, it's been donated to open source later on. So if you guys know SQL, it probably looks pretty familiar to you. So we're just specifying what is the expected type of the columns in that CSV file or number of files that we have in the given location on HDFS. And we're also specifying the row delimiter, which in our case is a comma. And the very last parameter in that command is the actual HDFS path in which Hive should look for the data as we query it. Well, it wouldn't be really easy to do it from the command line, so commercial distributions like Cloudera or Hortonworks also ship with a web interface. In case of Cloudera, it's called Hue, and Hue allows you to do like interactive SQL queries just as you would do in a SQL developer for Oracle, for instance. And Hue is not only about the Hive queries, it's also an interactive file browser and lets you define Oozie workflows, which we're gonna talk about just in a sec. So now that we know how to query our data and we've imported some example to HDFS, let's orchestrate it. So as defined in our business case, the account records will be ingested on a daily basis. And for that, there's a dedicated project called Apache Oozie. And Oozie ships with two features. One is, as I mentioned, a workflow definition language, which is an XML, and also so-called coordinators, which let you schedule those workflows and execute them on the cluster. Of course, you can write just pure XML, but if you're more a fan of interactive tools, you can also utilize the one which ships with Hue. And it lets you just drag and drop certain actions, which can be a Sqoop job, a Spark job, and an HDFS operation, so anything you would normally run on Hadoop. And once you save it and execute it, it's being automatically translated to an XML, which you can then run from a command line as well. All right, so we've gone through our initial challenge, which was the ingestion of data, querying it, and a daily orchestration of the process. So we have our, let's say, high-level rough architecture picture, but there are still some things left for implementation. And of course, I'm talking about the transfer and the ATM deposits data being streamed to the cluster. Now, we've used Sqoop, but Sqoop doesn't work with streaming, so it's just it was implemented in mind for batches, so for batch operations. And when it comes to streaming, there are different tools that are usually utilized to achieve that effect. So speaking of streaming, there's a certain message queue project that has gained a lot of traction in the recent years, and it's Apache Kafka. So what Kafka is, it's a distributed and scalable message queue, which is now being shipped with most commercial distributions of Hadoop. And actually, Kafka has its roots at LinkedIn, so it was initially developed there. And just like Hive, it's been donated to the open source, and it's now a full-blown Apache project with a really big community behind it. So for the sake of our example, our demo, let's just assume that our backend system is automatically pushing messages to that queue whenever something new arrives to our backend system. So once it lands in the message queue, what can we do with that? If we want to do just a simple ingestion from Kafka directly to HDFS, the easiest and out-of-the-box solution is Apache Flume. What Flume does is it's an agent that runs within the cluster, and once you configure its source, which in our case would be a Kafka message queue, and its sink, which would be an HDFS directory, it runs automatically in the background, and every time something new appears in Kafka, it will be automatically transferred to our HDFS directory. So no coding required here as well. However, if we would like to have some more complex processing of our streaming data, let's say we would like to filter out some records, we would like to do some transformations, conversion to a different format, doing some purification of our incoming data, then for sure writing some code, probably in Scala in Spark streaming would be essential here. And in that case, that would be the way to go. Of course, there are some other tools we could use, but I'm just showing you the most popular ones and the ones most commonly used. Okay, so for the sake of the example, let's assume that we want to just transfer all the records related to transfers and ATM deposits to our cluster. So we're gonna stick with Kafka and Flume. So we have data on transfers and ATM deposits being streamed to our cluster, let's say in close to real time. And now the very last part that we have left is the implementation of the Spark job, which will do the actual export from Hadoop to the external table in the database. Here is called AML cases. All right, so let's go through the Scala code. Actually, when it comes to Spark, it's not only about Scala, so that's not the only programming language in which you can write the Spark applications. However, this is the preferred programming language in the community. Spark was initially written in Scala, and whenever there are any new releases, the API for Scala is probably the most up-to-date one. And you can also do it in Java and Python. So if you're not really a fan of Scala, you can also do so. But today I'm going to show you some Scala examples. So if we would skip the boilerplate code in our Spark application, we would have to begin our code with creating so-called SQL context object, which would be an instance of a Hive context. And this will be an object in our Scala code which will allow us to query Hive tables which we have previously created. So instead of actually writing the Scala and Spark code, which would just browse our files on HDFS, do the filtering and so on, we can just create a Hive query and save a lot of time for us. Following the instantiation of the SQL context, there's an implicit import, which is going to help us with casting the column types in the workflows to the Spark SQL column object. Following that, there's the actual query to Hive, so the line number 4, where we have an object called ATM deposits. So what we're doing here, we're creating a query to Hive. We want to select the ID of the actual transaction, the account ID of the customer related to that deposit, amount of the deposit, and the timestamp. Let's just assume that when it comes to some money laundering related stuff, it's not that common for people to make really big deposits of cash, because when it comes to that amounts of money, people usually wire it. So that's why if you make big deposits of cash, it might be a little suspicious to the bank. So if you do so, you may receive a call from the bank in order to explain that. And this is a case which we would like to report to our external system, for example, that our analysts in the bank are using. So once we retrieve those records with the deposit amount larger than 10K, we're also going to hard code an extra column called type and put a value of ATM deposit there. Now going back to the transfers. So let's now say that we have another Hive table called suspicious, which holds all the suspicions IBAN numbers, let's say, of any identified fake companies that were used for money laundering in the past, and this is something which we want to monitor. So we're making that query to Hive to retrieve those IBAN numbers, and we're saving it to the object called suspicious IBANs, which is also an instance of a data frame, which is a data abstraction layer in Spark. Follow that, there's another data frame called transfers, which we are creating based on another Hive query. And here, in that case, we're only focusing on the outgoing transfers of our customers. So we want the ones with the negative amount, so the ones that actually build the accounts of our customers. And once we retrieve that, we're joining it with another data frame which we created before, the suspicious IBANs. So the outcome of the records in that data frame will be only those transfers which were directed to potentially suspicious account numbers. And like before, we're also hard coding an extra column called type, but here we're naming it transfer. And because both of the data frames, the ATM deposits and the transfers, have exactly the same structure, we can do just a union all operation on them, just as we would do in SQL. And from there, we can just save it on HDFS. So once the Spark job finishes, we're able to query it using a simple cat command, just like in Unix, but using it Hadoop API equivalent. And using Sqoop, again, we can export it to our external database. And of course, if we wanted to make it a recurring process, we can wrap the whole process in an Oozie workflow. So that would be it when it comes to our Spark job and how we were able to tackle that. That would be it when it comes to our business cases. So we had a couple of input tables in our backend systems. So when it comes to the account records, as the requirement was not to have it streamed to Hadoop, it was perfectly fine to use Sqoop for that. And another thing you should remember that probably if you want it streamed to the cluster, you should probably stick with another tools like Kafka or Flume. When it comes to orchestration, we used Apache Oozie, which is, as I said, the preferred project when it comes to orchestration, but it's not actually always used in the enterprises. Like at Nordia, for instance, although we do have Oozie in our Cloudera distribution, there's just another external enterprise scheduler which are using, called UC4 by Atomic, and this is perfectly fine. It's often a case in enterprises that there's a certain software that is widely approved among the whole corporation and is just adopted and it's been around for years. And another example is, for instance, Netflix, which doesn't use Oozie but use another scheduler called Tivoli. But under the hood, most of the Hadoop architectures end up using the same tools, which is Hive, Spark, and so on. Okay, so maybe one last comment regarding that architecture is that what I have presented to you is obviously not a silver bullet. So there's a number of ways which you could implement it, and just for the sake of examples, there was a limited of most commonly used Apache projects in the Hadoop ecosystem. Now one last thing I wanted to mention before I close up are the Hadoop file formats. So in order to keep things easy, throughout the demo, I only used textual formats on Hadoop. And Hadoop, just like any other file system, is capable of storing files of any format. However, using actually the textual files is not recommended. Actually, choosing the right file format may be really critical for your performance. There's a number of open source Apache projects related to file formats, and examples of them are, for instance, Avro and Parquet. So what's the difference between all of those? So when it comes to the textual formats like XML, JSON, or CSV, obviously they're not binary format. And one important characteristic behind them is that they are not splittable. What does it mean? Let's say that we would have a huge file on the Hadoop cluster that weighs, let's say, 1 terabyte. And obviously it wouldn't be efficient for our data node to process the whole file just by its own. It would be much more efficient to split the file and have many data nodes do the work for us instead of just one. If we're going to use an unsplittable format, that won't happen. That's why textual formats are not recommended on Hadoop. So when it comes to Apache Avro, it's actually the best multi-purpose storage format within Hadoop, and it's a really good starting point. So it's a binary format which has a JSON schema and supports also schema evolution, which means that, let's say you have a certain format of your data which you're importing from a database to Hadoop, and it can change over time. And supporting schema evolution means that at some point you might add an extra column or change its type, and Avro is gonna support it. So if you have a Hive table built on top Apache Avro files, you'll be able to read both the files in the old format and the ones in the newer ones. There's also Apache Parquet, which is a column-based format, which means it will probably be more efficient if you're just selecting a subset of columns from your files. Unlike Avro, which is row-based, which will probably be more efficient if you're just selecting all of the columns from Hive. So definitely a lot of things to consider when it comes to choosing the right format, like this supporting schema evolution, the requirements we have for write, read, and query, and its storage. And there's, when it comes to storage, as you can also tell, textual files have the worst performance, so they end up taking the most space on the cluster. If you're going with Avro, you're going to save some space, and when you use Parquet, you can save up even more. So that's definitely something you need to consider. And there's also a number of compression algorithms like Snappy, which you can use before you save your data to Hadoop. And there's also interesting fact about compression and Hadoop. So of course, compression is something that adds extra overhead whenever you write your data to the cluster or you read it from the cluster for processing. But when it comes to Hadoop, it can actually turn out that adding compression will increase performance because there are a lot of network-related aspects in the cluster. So there is a lot of data being transferred over the network. And actually, you may end up increasing your performance if you add some compression to your process. So that is all I wanted to share with you today. I'll be hanging around probably until 4 today. So come by, say hi, and if you have any questions or would like to discuss something, let me know. You can also shoot me an email or find me on LinkedIn. Thank you very much, guys.
Komputer.